Hey there, hi there, ho there. Welcome back. Scenery change. Let's continue our conversation about Mesozoic geology, and let's talk about what was going on out in the west, in the western uplift. But before we do, let me give you part of the super secret code. It is the number 4. It is the number 4. One more time, the number 4. Excuse me. Okay. The western region of the U.S. is during this time is really dominated by the Cordilleran mobile belt and the creation of the mountains of the West Coast. That really dominated kind of this time period. There was a change in boundary. More on that here in a little bit. So that was going on. There was a more eastward tilting subduction of an oceanic plate known as the Farallon Plate going under the North American Plate, which caused a ruckus, if you will. The deformation, one would think, when there's a convergent boundary like what we had here, as island arcs were kind of being sutured on, you would think the deformation would stay near the coastal region. But in fact, because of the change of what was going on with the Farallon Plate as it's being subducted, more on this in a little bit, we actually start to see deformation not just on the coast, but actually further inland, further east. So the first orogenic event during this Mesozoic era was the Sonoma Orogeny. It occurred right near the Permian-Triassic boundary, so right as we're getting into the Mesozoic era. And kind of like the Antler Orogeny, it resulted in a island arc kind of being sutured on to the western edge of North America. So we've seen things like this. And then, so this happened kind of, again, early on in the Mesozoic. Early on in the Mesozoic. The Cordilleran stuff kind of happened late Mesozoic. More on that again in just a second. So here's some of these island arcs that got kind of pushed on to the North American craton, these terrains that were added to it. But at this time, this was a continental crust and continental crust convergent boundary. I had mentioned just a slide back that there was a change in boundary because all of this stuff is converging onto North America, or with North America. Behind this continental crust, once this gets kind of pushed into the craton, behind it we have oceanic crust. So we're going to get a little bit of a different boundary type happening there. So let's see what this kind of looks like. So here we have the Sonoma Orogeny, these island arc terrains kind of getting pushed onto North America. And you can start to see the beginnings of some mountainous coasts on the west coast, or mountainous regions on the west coast, excuse me. So again, once this occurred, once the Sonoma Orogeny kind of pushed onto and accreted onto the North American craton, then the boundary changed from continental crust to continental crust convergent boundary to an oceanic crust to continental crust convergent boundary. So we had a little bit of a switch there, and then we get different things happening. Continental crust and continental crust have the same density. When they kind of collide, they just tend to crumple up, and we get mountains like what we see here. But oceanic crust is a little bit more dense, so when continental crust converge with oceanic crust, the oceanic crust gets pushed down back into the mantle, and we get some different type of tectonics happening, as opposed to continental to continental convergent boundaries. And we talked about that a long time ago. What was that, Unit 2 maybe? So all of this kind of started to occur during the later parts of the Triassic, the first period in the Mesozoic. This change in boundary really controlled the Cordilleran tectonics for the rest of the Mesozoic. So again, we went from continental to continental crust convergent boundary to oceanic crust to continental crust convergent boundary. And we had the Farallon Plate. That was the plate that was being subducted. And because of that, again, we get some different types of activity. We still get mountain orogenic events, but it just took a little different angle from it. I tell you what, let me give you another part of the super secret code. It is the number 5. It is the number 5. You got me? The number 5. So anyway, here's the Farallon plate being subducted underneath North American plate. The Farallon plate no longer exists because at this divergent boundary, which was pushing the Farallon plate into North America, so converging with the North American plate, the Farallon plate actually got subducted all the way under North American plate, and it does not exist anymore. We now only have the Pacific plate off of the North American plate, as well as the tiny little Juan de Fuca plate. So, again, the Sonoma Orogeny was back here at the boundary of the Permian and Triassic. But the actual Cordilleran orogenic activity that we consider kind of one lump thing, even though it was 3 separate orogenies, that occurred starting mid-Jurassic through the Cretaceous and even into the Cenozoic era. During the Paleozoic era, the time before this, in the Paleozoic, the West Coast really didn't experience too much in the form of plate tectonics and the outcome of that. This orogenic activity caused a thickening of the crust on the West Coast, and again, you get a bunch of these island arc terrains accreted, as well as little microplates kind of accreted onto North America, so it plays a big significant role here. Again, these were kind of 3 different orogenies, but we can kind of consider them all. They were all overlapping. Kind of, we had 1, 2, 3. They're all kind of happening at the same time, all driven by this oceanic to continental crust convergent boundary. So I'll kind of fast forward from the middle Jurassic through the end of the Cretaceous, and you'll just watch these island arcs getting accreted onto this portion of North America, and seeing the mountains rise and rise until we get something that looks kind of like this. And so, all of that was all of these orogenies. That was the Nevadan, that was the Sevier, and the Laramide, all occurring kind of back to back to back to back. Well, there should only be 3 back-to-backs from the Jurassic through the Cretaceous. As North America was moving westward, and it was overriding and pushing down the Farallon plate, which was moving eastward, the Atlantic Ocean basin was opening up. That's actually what was pushing the North American plate over on the east side. We had that divergent boundary. The Atlantic Ocean is opening up, and so the North American plate is kind of cruising off to the west. As that easterly dipping Farallon plate was being subducted, large volumes of granitic magma were generating as that plate was going down into the melting and creating a lot of granitic magma. These granitic masses kind of ascended as huge batholiths. If you remember, so granite is an intrusive plutonic igneous rock. A batholith is a large blob of igneous magma that cooled and formed this big blob of hard igneous rock. For instance, granite. All right? So you're getting a bunch of these granitic masses kind of ascending and getting kind of, occurring first. You get the magma melting from the plate subducting. You get the magma bubbling up, and then as the orogeny continues, these big blobs of cooled rock kind of get pushed up to create these really hard granitic mountains, such as what we see in the Sierra Nevadas, southern California, as well as into Idaho. So these are all kind of large batholiths that would later then also get pushed up during this orogenic event to form kind of these big mountains. This plutonic activity, and I mentioned it very briefly before, by the late Cretaceous, most of the volcanic and plutonic activity actually migrated eastward into Nevada and Idaho. The migration was caused by, we think, hypothesized, the changing of the angle at which the Farallon plate was being subducted. So we had the Farallon plate being subducted like this, which would melt and kind of have volcanics and plutonic activity, right near the coast. So, but if that Farallon plate, the angle of it changed, it wouldn't melt. It's not getting further into the Earth until way over here. So now, way over here, we're getting volcanics and plutonic activity pushing stuff more eastward. So that's what this is getting at. So initially, again, you had the Farallon plate here, igneous activity, more so right on the coast. But that plate then became a little more shallow. I'm being very dramatic. Let's say before the Farallon plate was dipping down like this. Now it's kind of dipping more like this. So now it's not melting until further in. So now you're creating uplift more eastward. That becomes very, very important here momentarily. So getting into the Sevier Orogeny, very similar to the Nevadan Orogeny. Thrusting occurred, pushing stuff, material breaking on the coast and stuff getting pushed up onto the land. That continued even more and more and more, even more eastward as more stuff is kind of hitting the side of North America. Things are getting crumpled up more and more and more further east. Again, the further subduction of the Farallon plate resulted in numerous overlapping thrust faults, where parts of the crust were kind of breaking and getting thrust up over the one another. Older rocks were being thrust up when this kind of stuff occurred. And all this deformation resulted in crustal shortening. So by all of this pressure, all of these things kind of hitting the side of North America, it actually resulted in crustal shortening, meaning things got crumpled up a little bit. So this area went from this to like this, because everything was just kept pushing in and kind of pushing in on it. So here's some of those thrust faults. Again, as this convergence continues, the crust starts to break. This material kind of gets pushed up and into and further eastward as we're continuing in the Sevier Orogeny, and then finally into the Laramide Orogeny. It actually developed east of the Sevier Orogenic belt. Whereas before all this stuff was pretty much adding on the west side, now all of a sudden we get some orogenic activity on the east side, and that's what's responsible for the present-day Rocky Mountains that we see in New Mexico, Colorado, and into Wyoming. Most of the features of the present-day Rocky Mountains resulted from the Cenozoic phase of the Laramide Orogeny, the half that's in the Cenozoic, to kind of finish out the Rocky Mountains, but the beginning of it definitely started into the Cretaceous and bordering the end of the Mesozoic and the beginning of the Cenozoic. You know what? What the hell? Before we go, let me give you another part of the super secret code. It is the number, what is it? Number 6. How about that? The number 6. One more time, the number 6. So let me give you a little visual of the change in the Farallon plate and how that changed the Cordilleran area and the geology therein. So initially we had the Farallon plate kind of dipping down here, right? And once it gets to kind of around this spot, this is the point where things start to melt, magma bubbles up, you have igneous activity, you have volcanism or plutonic activity, and this is what helped to push up the Sierra Nevadas, which are granite batholiths, as this continues to kind of push on the crust. Again, these things kind of get pushed up, and that's, again, how the Sierra Nevadas were formed during the Sevier Orogeny. We had this overthrust area where, due to this pressure, parts of the crust were cracking and being pushed up. And again, not much over here. But once that angle changed, the melting spot, instead of being right over here, now is way over here. And so this is what fueled and pushed up the Rockies and in place those batholiths that would later become the Rockies in full as we get into the Cenozoic. Well, that's about it. Let's go ahead and pause there. But before we do, let me give you another part of the super secret code. It is 789. You got me? 789. One more time, 789. So when we come back, we'll talk about sedimentation in the West. See you in a second.